Hi class, today's lecture is about trigonometry integrals, or you can say that it's about the integration of trigonometry functions. We are talking about all six of them here: sine, cosine, tan, secant, cosecant, and cotan. After the midterm, since we started learning about the integration, we have seen these trig functions showing up in our integrals several times. The first time that we saw these trig functions are probably when we first looked at the basic integration table. You know, when we first saw that integration of cosine equal to sine, or integration of sine equal to minus cosine, and so on, those basic stuff. After that, we saw these trig functions showing up again when we learned about the integration by parts. If you can recall, when it comes to by parts, we usually use this technique when we encounter this one distinct pattern of two functions multiplied together, like fx and gx. And when we learned about that, sometimes one of them is a trig function. And that was the second time, I think, that we saw these trig functions in our integrals. Today, we are going to look at them again in more details, which means that it's going to be a little bit more difficult, more challenging, and of course more fun to everyone here. So let's take a look at them now. Now let's move to the first slide. These are the some examples of trigonometry integrals. I put 6 of them here because even though they are all trigonometry functions, they have different pattern, they have different forms, and most of the time they require different technique in order to solve. All right, so let's take a look at this one by one to get familiarized with the trigonometry integrals. So let's start with the first one. You can see that this is just basic stuff. It's about integration of sine 3x. So in order to solve this, all we need to do is to look up the basic integration table, and we know that this is going to be equal to integrate of sine. It becomes minus cosine, and the inside stays the same. And of course we have to apply the inverse chain rule, and we are going to get this 1/3 out of that integration. And when we talk about this one, the solution method that we used is the basic integration. So let's make a note here. This is just basic stuff. Basic integration. All right. Now, next one. Oh, by the way, most of this we have done before. But we are going to look at them again and talk about the solution method so that we can review ourselves about what we need to do in order to solve them. All right, and you're going to see that each one is different. Okay, here we have this trig function sine, but it doesn't come alone. It comes with the another function right here. So if you look at this, we can see that we have one function in the front, and that's polynomial, and it multiplies with another function, which is a trig function at the back. So what we see here is this pattern, fx times gx. And when we see this kind of pattern, it's likely that integration by parts is the way to go. But I just want to emphasize the word likely here. Not always. Sometimes you don't need integration by parts to solve this pattern. Sometimes substitution works as well. But we have done this before, and we learned that in this case we use integration by parts in order to solve. Integration by parts. And once again, don't forget to check the basic substitutions, because sometimes applying this basic technique can solve the problem just fine, and you don't need to spend more time on advanced and time-consuming technique like by parts. So Here, make a note, always check basic substitution first. And if you find out that basic sub fails, then you can try the by parts. Now let's move to number 3. We have done this example in the lecture, and it was long, right? So I'm going to talk about this one again very quickly. In order to solve this basic integration, I wouldn't say basic, it looks basic, but in terms of solving, it's not. And the reason is, in order to solve this integration of secant to the power of 3, we need 4 different techniques. All right. So the first technique that we need for this integrals is integration by parts. 2, after we perform the by parts, we also need to apply the rearrangement technique. When we talk about rearrangement, it's about moving things around, moving terms around in order to show some certain pattern. The pattern that we can just look up the table and apply the integration. All right, so we rearrange to make it look nicer, to make it solvable. Now, after rearrangement, sometimes you need to apply trigonometry identity in order to change the form. Trig identity. Okay, for number 3, we have done this. I think it's last Monday. So if you want to know about the details of this particular example, please look up the old lecture. And the last one, 4, in the end, we also have to apply the basic sub too. Basic substitution. And the reason I brought this example here is to remind you that sometimes you need a combination of techniques. You need multiple techniques in order to solve some integrals. So we can make a note here. This is about multiple techniques. Okay, now let's move to 4 and 5 all together. And the reason I want to talk about 2 of them together is because 2 of them has similar pattern. And if you can notice from 4 and 5, they look about the same in the way that it's about the integration of sine or cosine, just like number 4 here. We have this cosine and sine. The only difference between 4 and 5 is the even and odd property of the power. Here we have this even power for number 4. So let's make a note here. We are looking at integration of trig function, sine and cosine with even power. And for number 5, we are looking at sine and cosine with odd power. I just want you to keep in mind that when it comes to integration of trigonometry functions, the property of the power plays a very important role. By being even and odd, it makes you having to use different technique in order to find a solution. Okay, so in this case, when the power is even, you need this technique called half angle identity. Keep in mind that when you encounter power that is even, you apply this half angle identity. And when we talk about this half angle identity, it's about this. Sine of x square equal to 1 over 2, 1 minus cosine 2x. And we have this cosine x square equal to 1 over 2, 1 plus cosine 2x. The reason that we call this half angle is because of the relation between the left hand side and the right hand side of the equation. So on the left hand side, the angle is just x, but on the other side is 2 times as big, and that's 2x. So x and 2x. Okay, even power, we apply this half angle identity. The reason that we want to use this is to basically we want to reduce the power from higher number to lower number. So we want this to happen 4, and we want to cut this to 2, and we can do that by using this relation. This, you have power of 2, but after you apply this identity, you have a power of 1 right here. Okay, and after 2, we want to cut it again and to make it 1. And we want this so much because when the power of the trigonometry is 1, it becomes easy to perform the integration, as you can see here. If we need to perform the integration of sine with the power of 1, it's easy to do, right? It's about looking at the table. But when it's 4, like in number 4 like this, not so simple. And that's why we want this to happen. We want to reduce the power to 1. Same here, 4 to 2 and to 1. That's our main goal for even power. All right? But on the other hand, when the power is odd, we cannot use this half angle identity. We have to use a different technique, and I'm going to call it STS. I made this up, but I like it because it's easier to memorize. STS. The first S is split. T is transform. Split, transform, and the last S, substitution. Substitution. All right. So let's see what happens here about this STS. So the first thing you need to do with this odd power of trigonometry function is to split one factor out. So step 1, split, is going to be cosine of x to the power of 3. You want to split one factor out like this, cosine of x, and then you have this, the rest of the terms right here, cosine of x squared. So what you did here is to split this out. Okay, this is S. Okay, and what about t? T, you are going to transform the rest of the terms, this cosine squared, to sine. You want to transform this to sine, and to do that you can use this trigonometry identity, which is sine of x squared. Oh, I should use this, I'm sorry. Transform, we want to transform cosine to sine. So we want to make cosine of x squared equal to 1 minus sine of x squared. We just need to substitute this into the cosine x squared. Alright? And after that, you need to perform another technique. And the last one, we have done this, ST. And the last one you need to do is another S, which is substitution. And S here, substitution, we need to make u equal to sine of x. with these 3 steps, you can solve these integrals systematically. All right. For the details, once again, look at the old lecture, and it's all there. Okay. Now let's move to number 6, and as you can see here, it's more complicated than the ones we have seen. It's sine and cosine. So what we looked at here is basically the combination of 4 and 5. All right. It's like we want to make our life more difficult. And by the way, this is the main focus of today's lecture. We want to find the answer for this integrals. The integration of the first trigonometry function, trig 1, in terms of x, and multiplied by another trig function, trig 2, in terms of x, and don't forget the x right here. And not just this, each trig function has its own power, and I'm going to call the first power for trig 1 m, and trig 2 has the power of n. Make a note here, m and n can be even or odd. Can be anything, all right? And they don't have to be the same. All right, m can be, in this case, m is 3, n is 4. And I just want to make a note again here that even and odd property plays a very important role. Check even and odd property. Important role when it comes to the strategy that you need to use to solve the integrals. All right, keep in mind even and odd, very important. Now let's move to the next slide. So we see this this pattern again that we just wrote down. So we have this pattern that is our main goal of today. We want to find the answer for the integration of trig 1 to the power of m and trig 2 to the power of n. So you see this pattern, and if you go into the details of this, you can see that trig 1 can be any of the 6 trigonometry functions that we know, right? Sine, cosine, tan, secant, cosecant, cotan. So we are talking about 6 functions here, 6 possible functions. And then for trig 2, it can be any of the rest of the functions. So if you pick one, then the rest can be any of the rest of the 5. So it can be any of the 5 here, which means that we are talking about 30 variations of this form. Right? And I don't know if this is lucky or unlucky, but it turns out that we cannot solve all 30 of them. We can only solve just some of them, and the one that we want to solve is just the one in the slide 1, 2, and 3. So we are going to focus on just 3 variations. I'm sorry about that. 3 variations, 1, 2, and 3. And at this point, you can see that there is some special thing about the pairs that we picked from the 30 variations. So the first variation, you can see that it's sine and cosine. The second variation is tan and secant. Now the third variation is cotan and cosecant. At this point, do you notice anything about the pairs that we showed here? If you look closely, you can see that the pairs that we picked out from this 30, they have some sort of relationship between each other. Sine and cosine, tan and secant, cotan and cosecant. The fact is, they are related by differentiation and integration. So make a note here, can only solve the pairs that are related by diff and integration. Okay. Actually, we can solve the other pairs too, the other 28, but we can only do it by using numerical method. As far as I know, maybe sometimes there are other ways to solve other pairs, but I would choose the numerical methods. But for these three, we can solve them by using analytical calculation. So once again, you know that let's put the relationships between trig 1 and trig 2 here. Differentiation of sine equal to cosine, and there you go. You have this relation between sine and cosine in terms of diff and integration. Now you diff tan, you get secant x squared. And also if you diff secant, you get secant tan. And down here you diff cotan x, you get minus cosecant x squared. And just like above, you differentiate cosecant x, you get minus cosecant x and cotan x. You can see the relation between them, sine and cosine, tan secant, secant tan, cotan cosecant, and cosecant cotan. right here. Alright, so here in this lecture we are going to look into only three variations: sine, cosine, tan secant, and cotan cosecant. Now let's take a look at the first one, sine and cosine. Many of you might expect this to be easy, but it turns out that we have to use different kinds of methods just for this first variation. All right, so we have many cases, but I want to keep things simple. All right, so the first thing that we want to check out is about the even and odd property of m and n. All right, so first thing we do when you see this pattern, sine and cosine, is about checking whether m and n is even or odd. Check if even or odd. Okay, after checking, if it happens that one of them, at least one of them, is odd, it's gonna go to case 1. Okay, once again, if after you check at least one of them is odd, it's case 1. What I mean is that m is odd, or n is odd, or both is odd. That is case 1. And for case 1, we need one strategy to solve this, and that is STS, split, transform, and substitution. Okay, ST and S here. So if you found at M odd, N odd, or both odd, use case 1. All right, but if it turns out that none of them is odd, or basically both of them are even, you go with case 2, and this case 2 is the half angle identity. Half angle. At this point, you might notice that this is quite similar to what we did up here. Number 4, when the power is even, we use the oh sorry, when the power is even, we use the half angle. All right, and when the power is odd, we use the STS technique. Same thing here. If we notice any m or n that is odd, we use STS. And if none of them is odd, or you can say that both of them are even, we use the half angle identity. Same thing, same strategy. All right, now let's take a quick look at case 1. We are talking about m is odd, or n is odd, or both. So we have to go through this sub cases. So let's take a look at the first one, when m is odd. If m is odd, it means that the power of the sign is odd. So make a note here, m is odd means that power of sine of x is odd. So let's make an example here. Example, when sine of x has a power of, I'm gonna say 4. Oh, sorry, odd is, I put 3. Let's put 3 right here. Power is odd, 3. So if you see something like this, let's try to use the STS technique. The first thing we are going to do here is to split one factor of sine out. So this is going to happen. We are going to split one factor of sine out. And of course, the rest of the terms, the power becomes even because it reduces by 1, it becomes 2. That is the first thing we are going to do. After that, we are going to perform the transform, right? Split and then transform. The transform is going to apply to this sine square term, the rest of the terms after the split, and we are going to use this property, transform, to transform this to 1 minus cosine x squared. And after that, after you perform the transformation, you do the substitution. Last step, make u equal to cosine. And it's going to correspond to the trigonometry functions after the transformation. We transform it to cosine. So we have to substitute cosine in the integrals. Okay, so that is the first subcase. Now let's take a look at the second subcase. That is when the odd term is n. All right. So when the odd term is n, it means that the power of cosine is odd. And for example, when cosine is has the power of 5, something like this. So the first thing we are going to do is the same as above. We are going to split one factor out, one factor of cosine. So split one factor out, we are going to get cosine of x right here. And then the rest of the terms, we are going to have a power that is decreased by 1. So we have cosine of x to the power of 4. All right, from cosine to the power of 5, we got to here. And after that, we will do the transform right here. And transform right here, we want to transform the rest of the terms, which is cosine to cosine of x to the power of 4 to sine. So we want to use this, in this case, cosine of x squared equal to 1 minus sine of x squared. We want to transform cosine to sine in this case, right? Which is the opposite of the subcase 1. We transform sine to cosine, but here we transform cosine to sine. So here, this is going to happen. It's going to be, well, I'm going to put everything here. 1 minus sine of x squared So this is going to be cosine x squared. So I put 2 right here, and that should become cosine of x to the power of 4 times cosine of x, the one that we split out in the first place. After that, we apply the last step, substitution. We substitute with the power, with the new trigonometry function that we got here. And we want to make u equal to sine of x. So in the end, we have this 1 minus u squared times cosine of x. Don't worry about this cosine of x. It's going to get cancelled later. We split it out for a reason. Okay, now let's put this one right here. This is going to be u squared. Oh, this is supposed to be u squared, I'm sorry. And this is supposed to be u squared times sine of x. Okay, same strategy as TS, split, transform, and substitution. Now the question is, what about the case when both of them are odd? Like this, both of them are odd. For example, we have this sine of x to the power of 3 times cosine of x to the power of 5. The question is, what are we going to do here? Both are odd. The best way to deal with this is to pick the one with the lower number, with the smaller number of the power, all right, to work on. So in this case, you pick the one with the smaller power. In this case, it would be sine x to the power of 3. And then after that, you perform the same strategy, that is the STS technique. All right. So it's the same thing, except that you have to pick one of them in the first place. And that is it for the case 1, when one of the power or both is odd. So the key point is this, power being odd. Okay, now case 2, when both m and n are even, or you can say that none is odd. The strategy that you need to use here is the half angle property. So you are going to pick the one of the trigonometry functions and apply this identity in order to reduce the power to as low as we can, hopefully to be 1. Okay, that's a lot of guideline we are talking about here. What about we use them in actual examples that might make more sense? Okay? So let's take a look at example 1. So we have this integration of two trigonometry functions, and we can see that one of them is sine and the other is cosine, and each one of them has its own power. Sine has the power of 3 and cosine has the power of 4. The first thing we notice is that sine and cosine is related by differentiation and integration. So this is one of the variation that we can solve. That's a good news. Now, we can use the guideline in the previous slide in order to solve this. Make a note here, sine and cosine are related by diff, or you can say I should use or, by diff or integration. And that's why we can use the strategy in this lecture. Now, back to this guideline. So many things to consider, right? Let's forget about that. Let's follow this this solution method. The first thing I'm going to do here is to look for the power that is odd. Number 1, always look for the power that is odd. That is the first thing you want to do. look for odd power. If you found one, like this, one of them is fine, or both is fine too. If you found one, it means that you have to use the first strategy, the case one. All right. Now, this, we can see that sine of x has the power of 3, that is odd. It means that this is case 1. Case 1. And in case 1, the strategy is STS. Split, transform, and substitution. Now we know what to do. Okay, so let's work on this. Integration of sine of x cubed cosine of x to the 4th. Alright, we are going to split one of the sine terms out. Alright, first s, split, so this is what happens. Same integration, but we split one of the sine out right here, which means that the rest of the terms is sine of x to the power of 2, decreases by 1. And cosine right here, still the same, nothing changes. Okay, and that is the first thing we want to try to do here. Now keep in mind that we split it out for a reason, and we expect this to get cancelled later. Make a note here, expect this, expected to get cancelled later. Let's see if that's going to happen. So, split is done right here, split. Already done, split, not spit. I'm sorry. Okay, split. Okay, now the next thing we are going to do is to apply the t step, which is the transform. And in this case, we want to transform this sine of x squared to cosine. And in order to do that, we want to use this trig identity, which is cosine of which is sine of x squared equal to 1 minus cosine of x squared. And this is the second step, which is the transform. So here we have this. It used to be sine x squared, but we are going to use this property. So substitute this in and we get this. 1 minus cosine of x squared. Alright. And here cosine of x to the power of 4 stays the same. We don't need to work on that or mess with that at all. Right? Sine of x still there and dx. Okay? Now we are going somewhere. Split is done, transform is done, and now the last step, the last s, which is the substitution. So we want to do substitution here, substitution. And in this case, we want to substitute the new trigonometry function, which is cosine. So here we want to make u equal to cosine of x. And we want to sub this back to our integrals. Oh, before you do that, don't forget to perform the differentiation here. Du by dx equal to minus sine of x. Alright, which means that dx is equal to du divided by minus sine of x. Okay, now let's put everything back into the integrals. Substitution, all right? 1 minus cosine of x squared, and we can see that u equal to cosine of x, so this becomes u squared. Cosine of x to the power of 4, we use the substitution, this becomes u to the power of 4. Sine of x still there, but then we want to substitute dx into, and we use this. And this dx equal to du divided by minus sine of x. And as we expected from earlier, we can see that this can cancel each other very nicely. Okay, so we split it out for a reason. We split it out in order to get canceled later. So now all you need to do is to arrange things, and we have this minus integration of 1 minus u squared, u to the power of 4 du. At this point it looks good because all the variable we have in this integrals is just u, so we can just perform the integration directly. So the first thing we are going to do here is to distribute u to the power of 4 in. This becomes u to the power of 4 minus u to the power of 6 du. Performing integration on this one should be easy because we only need to use the power rule. In the end, we have this minus u to the power of 5 divided by 5, the first term, minus u to the power of 7 divided by 7. And don't forget plus c right here. And once again, do not stop with the u in your answer because in the beginning we have this x variable. So put it back. Here we have u equal to cosine of x, so this becomes minus cosine of x to the power of 5 divided by 5. Looking at this, minus with the minus in front, it becomes plus. U to the power of 7, that is cosine of x to the power of 7, divided by 7, plus c. And that is the answer for this first example. And as you can see here, we started off by looking for the odd power. Alright, and that is the start that we have here, odd power. And we work on this sign. Alright, now let's take a look at one more. Once we got used to this guideline, it's going to become much easier. The first time around, it's going to be too many cases. I don't know what to do, right? But if you see some examples, it's going to get better. Now let's take a look at example number 2. We have this integration of cosine and sine. Cosine and sine, that's good. They are related by differentiation or integration, which means that we can use the guideline. Good news. Now, each of them has its own power, 3 and 6. And as I told you before, the first thing we are going to do is to look for odd power. Odd power, and we can see that the odd power is odd power term is cosine of 2x to the power of 3. The power for sine is 6, that's even, so we leave it alone. Right? Odd term, that's good. This is case 1. Case 1, and the strategy to solve this is 3-step. Split, transform, and substitution. Alright, so we are going to focus on the one with the odd power. So let's do that. So the first thing we are going to do here is to split one of the factor out. So this is going to be equal to integration, and we split one of the cosine out. It's going to show up right here, cosine of 2x. Now the rest of the terms of the cosine, the power decreases by 1, and that is cosine of 2x to the power of 2. For sine, it is not touched, so it's going to stay the same. That is going to be sine of 2x to the power of 6. Nothing changes. And done. First step, split. Okay. Now we move to the second step. We want to perform the transformation. And we are going to do with the terms that we just worked on, which is this. We see cosine 2x to the power of 2, which means that we want to transform this to sine. Transform trans to sine. Alright, so this is the second step. Transform. To transform cosine to sine, we just use this property, which is cosine 2x squared equal to 1 minus sine of 2x squared. Alright, so let's put this in. Integration of cosine 2x squared. Now, it's going to become 1 minus sine of 2x squared. This sine of 2x stays the same with the power of 6. Oh, I forgot this dx right here, so add it. Okay, this cosine 2x still there. And of course, we expect this to go away later, right? And then dx right here. Now, transform is done. The next thing is substitution, and we want to work on that. The terms that we just transformed. So substitution. And in this case, we want to put u equal to sine of 2x. Okay, so it's going to be a little bit different from the example one when u equal to cosine of x. But if you follow the guideline, you're going to see that why we have to use sine here. It's because that the term with the odd power is cosine. Alright, substitution, it means that we have to differentiate this du by dx equal to cosine of 2x, and chain rule, 2 in front. Move things around, dx is going to be equal to du divided by 2 cosine 2x. Okay, with this substitution preparation, we can just put everything back into the integrals. Now, here, integration of 1 minus sine 2x squared. We have this substitution, so here it's going to become u squared times sine 2x to the power of 6. Substitution again, this becomes u to the power of 6. Cosine of 2x still there, waiting to get cancelled. Now we have this dx last term, and we know that dx equal to du divided by 2 cosine 2x. So put things in, du divided by 2 cosine 2x. And as we expected, this cancels with that. Right? So after this, we just need to move things around. I'm going to get the constant outside of the integration. Inside we have 1 minus u squared times u to the power of 6 du. Alright, distribute u to the power of 6 in, you have u to the power of 6 minus u to the power of 8 du. At this point, performing the integration of this is easy, and as you know, this is going to be equal to 1 over 2 u to the power of 7 divided by 7 minus u to the power of 9 divided by 9 plus c. We never leave u like this for the final answer, so don't forget to put sine of 2x in from the substitution. So here we have sine of 2x to the power of 7 divided by 7, but we have this factor of 1 over 2 in front, so this is 14, minus u to the power of 9, that is sine of 2x to the power of 9 divided by 9 times 2, that is 18, plus c. And there you go. This is the answer for example 2. It's a little bit different from example 1 in terms of substitution and stuff, but if you follow these steps, you are going to see that it's the same strategy: split, transform, and substitution, right? Look for the odd power, and then you work on that by split first, and then you transform, and then you substitute. 3 steps. Alright, let's move to example 3. Okay. Now example 3, once again we see this combination of two trigonometry functions, and let's see how they look like. Here we have sine multiplied by cosine. Good. Related by diff and integration. Now the next thing we do here is to check the power of each one of them. And we can see that the power of the sine here is 2, and the power of the cosine is 2. I told you when we talked about the guideline that the first thing we do is to look for the odd power. And in this case, we can see that there is no odd power. So this is what we find out. No odd power. Because, well, both of them are even. And that is the key. That makes us having to change the strategy. No odd power means this is case 2 right away. Case 2. For case 2, it's not STS, it's not split, transform, substitution. We have to use something different, which is the half angle identity. Okay, for case 2, no odd power, it's going to be half angle identity. Okay, now let's work on this integrals. So here we have the integration of sine with the power of 2 and cosine of x with the power of 2, and we want to perform this half angle identity. But before we do that, let's take a look here. We have two trigonometry functions in our integrals, and you know when we have two of them, it's kind of hard to handle. It's going to be better if we can get rid one of the functions here, make all of them sine or make all of them cosine. So in this case, I'm going to start by doing the transformation. All right. Transform. I decided to change this sine x squared to cosine, and I can do that by using this. Sine of x squared equal to 1 minus cosine of x squared. Alright, so what happens here is I replace sine of x squared by 1 minus cosine of x squared. Alright, and this, oh, I need a lot of space here, so I need to save some space. Let me write this again. Okay, this is going to be equal to integration of 1 minus cosine of x squared and times cosine of x squared. As you can see here, at this point we only have cosine in our integrals. It looks more simple than having 2 in the line before that. So after this, we are going to perform the half angle identity. But before that, let's distribute the cosine of x squared outside in. This is going to be equal to cosine of x squared minus cosine of x to the power of 4. No more sine. Should be easier to deal with. Alright, at this point you can see that we have just cosine with the power of 2 and 4. We are going to apply the half angle identity here. Right, so let's use that half angle identity. We want to, well, our goal here is to make this 2 goes to 1, 4 here goes to 2, and to 1, just like we did before. So we are going to use this cosine of x squared equal to 1 over 2, 1 plus cosine of 2x. Okay? Now we can use this identity again for cosine of x to the power of 4, because we know that this is equal to cosine of x to the power of 2 and square again. With this we can replace the inside with the 1 minus, we can replace the inside with this. Right, that is cosine of x squared. So that's going to be 1 over 2 plus cosine of 2x to the power divided by 2. All of this has the power of 2 at the end. Okay, so let's continue with this. So this, I'm going to get 1 over 4 out. 1 over 2 for both of them, and it got square, so I can take it out and I perform, well, this should be better. I'm gonna take this out, take this outside. The inside is 1 over 2, so outside it got square, it becomes 1 over 4. Now I can perform the square of the 2 terms inside. That's going to be the front square plus 2 front back, that is 2 cosine 2x, plus back square, that is cosine of 2x square. Alright, now at this point you can see that we still have a problem here, because this power is still not 1. So we want to reduce this to 1, and we can do that by using this, because we know that cosine of 2x to the power of 2, it's going to be equal to 1 over 2, 1 plus cosine of 4x. So the angle is going to be twice as big as the one that we used before. Alright, so let's put this in. Here we have 1 over 4. Everything is the same, 1 plus 2 cosine 2x, plus before it was this, but now we are going to substitute this in. Here we have 1 over 2, 1 plus cosine 4x. Alright, so let's combine all the terms here. And we have this 1 over 4, the first constant, and we also have 1 over 8 Oh, I should do this step by step. All right. So that 1 over 4, that is the first term, and then the next term is cosine of 2x divided by 2. And after that, we have this 1 over 8, and we have this cosine of 4x divided by 8. Okay, so that all of this is going to be equal to cosine of x to the 4th. All right, at this point we have this. We have transformed this to the power of 1, and we have transformed cosine to the power of 4 to just cosine to the power of 1 and 1 here, so they look good. Now we are going to put everything back to our integral. Now let's look at here. Integration, before we had this cosine of x squared, but we don't like that. We want to transform this to 1, and we are going to use this. Put this in, and this becomes 1 over 2, 1 plus cosine of 2x. Alright, and this looks good because the power is just 1. Now minus cosine of x to the power of 4. We don't like that. Power is hard to deal with, so we are going to replace that with all the terms with the power of 1. So here we have this 1 over 4 plus 1 over 8. Well, I can use 5 over 8 here. Oh no, 3 over 8. Combine the terms, 3 over 8 plus cosine 2x over 2 plus cosine 4x over 8 dx. Now we put the big parentheses to all of them here. Okay, at this point, all we need to do is to combine all the terms. So I'm going to start with the constant. So here we have this 1 over 2 minus 3 over 8 plus cosine of 2x over 2 minus cosine of 2x over 2 minus cosine of 4x over 8, and we have to integrate this with respect to x. At this point you can see that this cancel with that, and 1 over 2 minus 3 over 8, you get 1 over 8, and the rest of the terms is cosine 4x divided by 8, and this has to be integrated with respect to x. So at this point you can see that it's quite easy to perform, right? So here, integrate 1 over 8, you get x over 8. Now minus, you need to integrate this. Cosine of 4x divided by 8, and good news, has a power of 1. All we need to do is to use basic integration. Integrate cosine, we get sine. And 4x stays the same. We still have this 8 down here, and with the reverse chain rule, we have 4 factor of 4 down here. And don't forget the plus c at the end. So to make things nicer, so just multiply them in. X over 8 minus sine of 4x divided by 32 plus c. Okay, so that is the answer for example 3. I brought 3 examples here because each one of them is different. The first thing, when you see this kind of combination, sine and cosine with some powers, the first thing is about finding the odd power, like that. If you found an odd power, you work with the STS strategy. Alright, just the same. For example 1, you work with the sine terms. Example 2, odd power again, but this time it's with the cosine term. So you apply the same STS with cosine. It's a little bit different, but the same strategy. But if it turns out that none of the power is odd, well, you can see here all of them is even, all of them are even. So in this case, you have to apply the half angle identity in order to solve. No STS here. Okay, for this lecture, I'm going to stop right here. I might add part 2 later, and that is going to be about the combination of secant and tan, which is the variation number 2 right here, and the cotan and cosecant variation 3. These two require the same strategy in order to solve, and it will be in the part 2 of this lecture. All right, I'm going to stop right here.